All right. So, in previous work, we introduced a technique known as lazy basic block versioning, which is a single pass code generation technique. The particularity of this is that it does on-the-fly type specialization, and it is intraprocedural only, so it works only within function bodies. In today's talk, I'm going to introduce 3 extensions to basic block versioning that aim to make the technique achieve interprocedural type specialization on the fly. We have prototyped and evaluated these extensions in Higgs, which is an experimental just-in-time compiler for JavaScript, which we've built from scratch. So lazy basic block versioning, introduced in previous work, works at a fine granularity. So it generates code one basic block at a time, as opposed to method-based code generation. It's lightweight and it works in a single pass. And it generates block versions lazily. So it generates machine code lazily and is able to compile only parts of a function that are actually executed. As we compile code, we accumulate facts, type information in particular, and we do this by leveraging implicit type checks. And basic blocks are specialized based on the known type information that we have accumulated so far. So we may compile multiple type specialized versions of basic blocks, but the point of the technique is not to duplicate basic blocks. The point is to specialize them. So dynamic type tests, the focus of our research is to eliminate as much dynamic type checks, as much dynamic type checking overhead as we possibly can. We're focused on dynamically typed language. In particular, we work with JavaScript. And basic block versioning uses the type checks that are implicitly part of the JavaScript semantics to extract type information. So JavaScript has these type checks that are implicitly part of the semantics of the language. That is, if you have an operation like x plus y, you could feed any values in JavaScript. So you could have a string plus null, a floating point plus an integer, the boolean true plus the string foo, and you would get some value as output. So inside the plus operator, there's an implicit type dispatch that goes on. For instance, you might check, is x an int32 value or not, and if x is an int32 and y is also an int32, then you do an int32 addition. So our implementation will use these type checks to extract type information and make it available at code generation time. So in Higgs, the values are separated based on type tags. For example, int32 are 32-bit integers in our implementation. Float64 are floating point doubles. So we have a type tag for JavaScript undefined value, one for null, booleans, strings, objects, arrays, and closures. So if we look at a simple example like a really trivial control flow graph like this one, at the top we check if n is an int32 value, and if it is an int32, we go to block B. If it is not int32, we go to block C, and afterwards we merge into block D. So trivially, if n is int32 at runtime, we'll go to block B, and we know that in block B, n has to be an int32 because we just executed this type check. In block C, we have that n is not an int32. But then when the control flow merges, we have that n is either int32 or not int32, so we know nothing at all. So what we could do is we could tail duplicate D into a block D prime and a block D prime prime in which we preserve the information that we know about D. Obviously, this is trivially not scalable. If you did this for every type check inside of your program, you would have a code size explosion. And you wouldn't get very far. So what we do is that we actually generate the basic block versions lazily. So if n is always an int32 at runtime, we will only generate the path on the left, where we preserve the information that we know about n. And what actually happens is that if n is always int32, we actually generate probably less code than if we had to generate both paths. So lazy block versioning compiles versions lazily when they are first executed, and only for the types in the type combinations that are actually seen at runtime. So the programmer's behavior ends up driving the versioning, and we do this by interleaving compilation and execution. So when we get to a type check that we cannot determine which way it will go at code generation time, we install machine code stubs and we let the program execution tell us which paths are actually executed. So we install stubs and we uninstall them when the stubs are executed. And by doing this, we can avoid compiling unneeded block versions. So for example, if you have some code that throws an exception, but at runtime that code is never executed, then we will never generate machine code for it. And we will never pollute type information based on an exception that is never shown, for instance. So if we look at a pretty simple example here, we have a function sum n that computes a sum s of values going from 0 to n exclusively. Now in JavaScript, the value n does not have to be an integer. You could actually feed in a floating point value or a string or a boolean or anything, and you would get some value as output. So we can't actually assume that n is going to be an integer and specialize codes based on that. But in this example, we have that we're calling sum of 500, which is an integer value. And so we could actually specialize this code. We could optimize it for this use case. So if we look at the control flow graph in our intermediate representation, it's going to look something like this, where on the first row we have the loop test, I is less than n. On the second row we have the addition of I to the sum, and on the third row we have the incrementation of the index variable I. So we have all these implicit type checks though. We have to check that I and n are integers before doing an integer less than comparison. If n was a string, we'd have to do a comparison of an integer with a string instead. On the second row, we have to check the types of s and I before adding them together, and so on. What we can achieve with lazy basic block versioning essentially is on the fly, we can hoist the type check on n outside of the loop body, and then when we call sum of 500, we will check that n is an integer, and afterwards we will stay inside of this optimized loop body where there are no type checks. So we check the type of n when entering the function only once. And how do we achieve this? Well, we do this by first creating a context when entering the function where we know that s and I are int32 values. We know this because we just initialize them to integer values. But when entering the function, we don't know what the type of n is. But then we execute, we will eliminate the first type check on I because we just initialized it. But we cannot eliminate the type check on n because we don't know what the type of n is when entering the function. But once we've executed this type check on n dynamically, we know that n is an int32 value. So we have that s, I, and n are all int32 values after this first type check. And then from this, we can eliminate the rest of the type checks inside of the loop body. And we have that s, I, and n remain int32 values so long as there are no integer overflows. But here again, dynamically, we know that there is no overflow because it doesn't happen. That's because we keep the overflow checks. So the results that we got from this technique were presented last year at eCoop 2015. We were able to eliminate 71% of dynamic type checks across our benchmarks. We had measurable speedups of about 21% on average, and a small average code size increase of 0.19%. The reason why the code size increase is so small is because laziness really helps us avoiding to generate unneeded codes, and also because specialized code, optimized code tends to be a little smaller. So the smaller optimized code makes up for the number of extra versions that we generate in a sense. But can we do even better than this? Well, today I'm going to present our extensions to make basic block versioning interprocedural. So if we look at a simple example like this, we have two recursive functions, a function makeList, which generates a linked list of integers, and a function sumList, which computes the sum of integer values in such a linked list. So intraprocedural basic block versioning does not optimize this code very effectively. So let's try to understand why. Well, the first reason is that what I've presented so far treats objects like black boxes. So every time we read a property from an object, we have to check its type over and over again, which is obviously very inefficient. And in JavaScript also, global variables are properties of a global object. So every time we access a global variable, we have to also check its type over and over again. And that applies to function calls too. Because in JavaScript, if you try to call something that happens to be a null value, you could throw an exception. So every time we call a function, we have to say, is this actually a function I'm calling, or do I have to throw an exception? Which we would like to avoid. Most JavaScript engines like Google V8, SunSpider, etc. represent JavaScript objects using this structure known as hidden classes. So hidden classes or shapes will separate the object layout representation from the actual in-memory storage of object property fields. So an object shape tells you which properties the object has and at what offset in memory they are stored. What we did is to simply extend shapes to annotate them with type information. So here property D is a null value, C is a string, B is a floating point number, etc. So we extend shapes to have type information, including type tags and also method identity. So if an object has a method, we know which function body this method would be. And then we do versioning based on shapes. So in the same way that we use implicit type checks to extract type tag information, we use the implicit shape test in JavaScript to extract object shape information. And this permits the elimination dynamically of missing property checks. So we can know that an object definitely has a property as opposed to might have a property. We can eliminate checks that verify, is this a normal property or a getter and setter? We can eliminate boxing and unboxing overheads, and we can also, in many cases, eliminate dynamic dispatch. We can know I'm calling method foo, and it is definitely this function foo. And on top of this, we've also implemented some interprocedural versioning relating to function calls. So previously, we propagated type information within function bodies only. But this wastes computation, especially for recursive functions, because you can imagine, say I have a trivial function like computing the Fibonacci numbers recursively. So the function Fibonacci calls itself. And so I get an integer number n, and then I do n minus 1, and that's also an integer, and then I call the function recursively. And then when I enter the recursive function call, I don't know anything about the parameter, so I have to check, is the parameter I just got also an integer? But that's kind of stupid, because in the caller, your argument was an integer, and in the callee, if you're interprocedural only, you have to check the type of the argument for every single call. So what would you like to do is to pass argument types to map argument types to function parameter types. And the way we do this is very obvious and simple in a sense, is that we simply create multiple specialized function entry points. So we create specialized versions of function entry points that have information about parameter types. And because type shapes allow us in many cases to know exactly which function we're calling, I can simply jump directly to the specialized function entry point in many cases without any dynamic dispatch. So the caller can jump directly to the exact specialized version of the callee when callee identity information is available. When I do not know which function I'm calling, I simply fall back to a generic function entry point, which is just what I was doing before, but this is actually rare in practice. On top of this, we also wanted to try to pass back information about return types. So when you're returning a value and you know its type in the callee, it would be nice if you could pass the return value type back to the caller, so that the caller doesn't have to recheck the type of the return value that you knew in the callee. But this is a little tricky because you can't apply the same strategy as entry point versioning. Because when you're in a caller and you know which function you're calling, you can jump directly to the specialized function entry point. But when you're in a callee function and you want to pass the information back to the caller, you have that one return point in a function could jump back to several callers. So you would need some dynamic dispatch to presumably pass return variable type. So how do you deal with this? Well, the way that we do it is that we use a speculative optimization strategy. So essentially, the first time that we return from a function, if we know the type of the value that we are returning, we speculate that the function will always return a value of this type. So if I'm in my Fibonacci function, I'm returning some integer, I speculate Fibonacci will probably always return integers. And then when I return back to the caller, I will lazily compile the continuation of this call. And I will optimize this based on the assumption that the return value is an integer. And execution will continue to proceed. And essentially, if the function ever happens to return something that is not an integer, I will have to invalidate my specialized continuations. So in our little example here, SumList that computes the sum of a list of integers, when the list has length 0, when it's only the null value, I return the int32 value 0. So then I can speculate that my SumList function always returns an int32 value. And then when I'm summing a list of length 1 or more, I will get an int32 value for a list of length 1, and then lst.val in this example is also always int32 dynamically. So my invariant is never violated, and I can keep executing my specialized code where I always get an int32 value. This strategy does not work, however, for the function makeList, because this function can return an object or null. So the first time that I execute it, it's going to return null. But if I generate a list of length 1 or more, I'll get an object back. So I'll have to de-optimize callers to this function. So how well does this all perform? Well, we've evaluated this on 26 programs from SunSpider and V8 Bench. We've compared the results of our extensions on tree configurations, basic block versioning with type shapes, basic block versioning with entry point versioning, basic block versioning with entry point versioning, and call continuation specialization. And we've compared that against plain unextended basic block versioning. The results that we got were that dynamically in 97.5% we can determine in our benchmarks the identity of callees. We successfully propagate return type information 72% of the time, and we are able to eliminate 94.3% of type checks with all of our extensions as opposed to 71%. And compared to interprocedural basic block versioning, our technique produces a worst case code size increase of 5.5%. The code compilation time increases by 3.7% in the worst case, and the execution time decreases by 37.6% on average. That is compared to a system, I believe, without basic block versioning. So another thing that we did is we were wondering how well this performs compared to a static program analysis. So what this graph shows is basic block versioning with all of our extensions in gray, and on the left we have a simulated program analysis. The way this analysis works is we record a profiling trace of the program, and afterwards we check which type checks always go the same way. So this is basically an upper bound of how well a static program analysis could perform. Essentially, if a type check always goes the same way, then we say a perfect analysis could remove this type check because it always went the same way. And then we do the same thing with basic block versioning, except we check how many type checks are actually executed at runtime. And what we have is that basic block versioning, on average, at the bottom right, performs a little better than a simulated perfect analysis. So you might ask, how is that even possible? How can you do better than a perfect analysis? Well, the difference is that basic block versioning, because it can separate and duplicate code paths, can transform the code. So some type checks that are present in the original program can be eliminated in a different way. That is, once you separate a code path, you might have a path where a type check is never executed, whereas in the original program, it did not always go the same way, if you follow what I'm saying. Okay, we've also compared our implementation against commercial JavaScript virtual machines. Obviously, Higgs does not perform as well as V8 and SpiderMonkey because we're missing a number of optimizations that they have. We have a really simple garbage collector. We have no loop invariant code motion or global value numbering. We do not have auto vectorization, bounce check elimination, method inlining, escape analysis, allocation syncing, etc. And we put floating point values in general purpose registers. We do not have floating point number register allocation. But despite this, we managed to outperform V8 on 3 out of 26 benchmarks and do 47% as fast. Yeah, and in conclusion, this technique has many possible applications, I believe. It could make for better baseline just-in-time compilers. It could be used to reduce gradual typing overhead, and possibly also in dynamic binary translation. Okay, so that's it.
So any questions for Maxime?
Yeah, did you compute what the overhead was? You had this like whatever 26% improvement, but how much penalty were you paying for that? You know, just in terms of all the extra runtime information.
By what do you mean exactly by penalty?
Just like you could have done an analysis where you just recorded all the additional information, but then didn't actually use it, and that would give you an idea of how much.
Do you mean so you mean the penalty of the type analysis?
Right, yeah, the runtime penalty you're paying. Because clearly you're getting an overall improvement, but I'm just curious how much you're paying to get that improvement. That's all.
Our system compiles about as fast, or maybe like 3% slower with basic block versioning, as opposed to when we completely disable basic block versioning. If you want to compare the performance of basic block versioning with respect to traditional type analysis, we perform, I don't know, an order of magnitude faster. I don't know exactly how much faster, but this technique is on the fly and in a single pass. So it's faster than pretty much any iterative type analysis you could possibly implement, as far as I know.
Did you check for any higher order types, like functions or a list of integers?
Well, when we represent function types, we will say, I know that this is a function, and we kind of have 2 degrees. We can say, I know this is a function, and I know it's a function, and I know it's this function body. So we have function identity information also. And when we represent object types, we have, I know this is an object, and I know this is an object with this shape. And once we know it's an object with a given shape, the shape also tells us it will have property A, B, and C that are entered to float string. But there is a limit to that, in the sense that this technique propagates information forward. And it does not do a fixed point. So if I have a linked list, I can say I know that I have a node that has an integer and a pointer to a next node, but I can't know that the next node is going to have a pointer to another next node or going to be the end of the list, because otherwise you get into a situation where you have a shape for a list of length 1, a shape for a list of length 2, 3, 4, 5, and you get an infinite number of shapes.
We do have time for one more quick question.
I find these improvement numbers very impressive. I was wondering whether there is a trend that smaller programs improve more than larger programs, because larger programs are less well behaved or less uniform.
Unfortunately, a projector is disconnected. Okay. Well, I skipped over the graphs because I didn't really have much time to go over them. I would say we perform extremely well on small programs because they're pretty simple. We do perform fairly well on some large programs. Like one of these benchmarks, early Boyer. Here, this is the number of type checks eliminated. So if you look at the middle of the first row, early Boyer is a functional benchmark. It's the largest one in the set, and it's an extremely heavy benchmark. And in this one, we managed to eliminate something like 90% of type checks with all our tricks. And we also perform better on this benchmark, significantly better than the simulated analysis. So I think it does scale fairly well. Obviously, there's a limit to these findings because we have a corpus of benchmarks that go up to maybe 5,000 lines. So I can only speculate about how well we perform on programs of 100,000 or a million lines of code, but I think it would still do pretty well.
All right, so let's thank again Maxime.